Many different reasons why we want to look into simulations, and therefore also many different tools around. This is just not a complete list, but just one list of MR simulators which are available on the internet. Some of these projects pretty old, some of them are newer. Not all of them are open, and I can only talk about the last, the second last, which is Dreamers, where I'm the, where I worked a lot with. The MRI lab, last one, is also an open source project, basically a MATLAB-based simulator. I think just from 2 years old, so a pretty recent one. So many different tools, each with different pros and cons, and most of them developed for one of those specific reasons I mentioned on the previous slide. Before coming back to this, I briefly talk about actually what are we doing here. So we're simulating the physics of MRI, and there are different approaches to the physics. The nice thing that is that actually every experiment you are interested in, nearly with 100% chance, is classical physics. So we don't need to understand quantum mechanics to understand MRI, which is in first place a good thing. So the things are not too difficult. We basically have just two simple equations which basically drive the whole thing. So the one is the Bloch equation, which basically is the physics of the single spin. How does it move? How in the magnetic field? And the other is a signal equation. How do actually all these spins add up to form an MR signal? So what we use in these simulations or in MRI is magnetic fields to manipulate the spins, and these are, of course, as you know, the gradients which encode spatial information, but that could be also more any off resonances. For example, you know, when we have distorted fields coming from air tissue boundaries, so these are susceptibility-induced distortions of the magnetic field. Of course, we have the transmit fields, which actually excites the spin system. So there are many different components to the MR field. If we simulate them, we typically do this in a specific coordinate frame, which actually rotates with the Larmor frequency. Then the simulation is, or the spin physics is basically a rotation around a so-called effective field, which is given by the excitation field and the off resonance present. The signal in the rotating frame is a demodulated signal, and in a movie that would typically look like this. So this is now simulating a gradient echo sequence, and now spins rephase, form an echo, and here they are all in phase. That's the gradient echo, and this is what we typically detect. The solving the signal equation, so the sum over all these spins, is typically a very straightforward thing, because when we have this classical simulation, this is each and every spin is basically independent of each other, is solved by a given, its dynamics is given by the Bloch equation, so we can compute the spin dynamics simultaneously, for example, on multiple CPUs or GPUs, and then collect the result at the very end and sum up. So that's basically what the signal equation is doing. However, the problem is that we need typically many spins to get a realistic simulation of MRI. And how many we need is actually not so easy to answer. So these are simulations of a very simple gradient echo sequence, very long TR of 5 seconds on the left, and we simulated 4 spins per voxel. If we now just decrease the TR below actually the T2 of that sample, which is 100 milliseconds, we get artifacts. And these artifacts are completely artificial, so you wouldn't see them in real life. If you increase the number of spins in the simulations, they get weaker, and finally they are gone. So that's a problematic thing about simulating MRI. Depending on the problem, it might get very difficult to make a realistic simulation involving, because many spins need to be involved. Yeah? So this is a two-dimensional simulation, but if you want to simulate a full 3D object, of course, many more spins will be required. So if we have to take into account many spins in a single imaging voxel, then simulations can get very lengthy. How many are needed, as you have seen in this example, cannot be answered in general, but depends on the problem. So let's just quickly do the math. So we want to solve this equation, the Bloch equation, simple differential equation, but for this very general driving field, magnetic field, consisting of gradients, off resonances, and the excitation field. There's no analytic solution for this mathematical problem, at least not in the general case. There are closed-form analytical solutions for specific cases, especially if there is no radio frequency pulse involved, and this is exactly the solution which is required for imaging for the actually after the excitation. Yeah? So in that, then the dynamics of the magnetization vector is this simple precession term, and this is then basically exactly the case-based description which which provides the basic of MRI. When we have a radio frequency pulse present, as for example here in this movie scene, so this is the very famous example of a so-called adiabatic inversion. So this is, for example, which gives nice T1 contrast and happens in the beginning of each and every MPRH sequence. Then things get more complicated, and there's not always an analytical solution present, only in a few cases. For example, when there's no off resonance, and this is a simple rotation again. If there is off resonance presence, then we can still assume that the longitudinal magnetization is not changing a lot. This is called the small tip angle approximation. And then we still have an analytical solution, which basically tells us that the RF pulse, the Fourier transform of the RF pulse, is actually the transverse magnetization as a function of the off resonance. So this is, you may have heard of that. So that's basically the slice profile, and slice profiles can be very nasty and very important, because sometimes magnetization leaks from one slice over to the next slice, and this is which is in the first place in small tip angle approximation. So if we have small flip angles approximated simply by Fourier transform. When it's getting when we use look into general RF pulse, then there's typically no analytic solution possible in general. So what we then can do is we can solve the Bloch equation numerically. There are typically two ways to do this. One is to use a so-called ODE integration, so solving the differential equation numerically, or the other option is to approximate the driving field using the analytical solution seen before. So first option is, use some state-of-the-art integrator. You may remember that from your math classes, that one prominent way to do this is so-called Runge-Kutta or a multi-step integrator. So what we basically do here, we follow the solution over time, and ideally we do this with some adaptive time stepping, depending on the error of what we're actually depending on the error of the solution. So we can use large steps, and then when the solution starts to change more rapidly, we see we will get a huge error. So then we better stick to smaller time steps to get an accurate solution. Yeah? So this can be done in many different ways, and actually you don't have to program things like this yourself. There are excellent libraries available in many programming languages. For example, in Python, this is done with the ODE int function, which is a general function to integrate differential equations. That is the one possibility. The other possibility, which is very often used in MRI, is the so-called half pulse approximation, which basically splits the excitation field, for example, sync pulse to select a rectangular slice, into small constant driving hard pulses, and therefore it's called hard pulse approximation. And what that reduces basically the problem to simple rotations, which can be chained up through multiplication of matrices, and this is either done with 3x3 rotation matrices, or more efficiently with so-called the Cayley-Klein matrices or quaternion approach. Also, that is is available in many different programming languages. So why is that important? Because then we can exactly simulate what happens under off resonances, and this is just to remind you what that means. If there is no off resonance, then we simply have rotation around the of the spin from equilibrium into the into the transverse plane. However, if there are off resonances around, then there will be no full rotation, and at large off resonances we will not generate any signal at all. So this is can be easily simulated with the three different approaches I presented before. For example, small tip angle approximation, numerical ODE integration, or the rotation matrices. This is comparing the three different approaches here, and this is basically showing the full movie starting from 0 degree flip angle and then going up to 180 degrees. Repeat the movie for small tip angles, all are same. For very large tip angles, you see that we need a numerical solution. Implementing something like this can be actually very helpful to understand the basics behind, and does not take actually a lot of effort. So this is a Python implementation of the example I just showed before. You can also find the code on my GitHub page if you're interested in. And of course, yeah, it's just a few lines of code, and of course can also do things like this with a few lines of code in MATLAB. So something like this is needed for a general purpose simulation of MRI, because things are, sorry, wrong direction, complicated in general. So when we now want to do a full simulation of an MRI sequence, this is, for example, an EPI sequence, we basically have two different approaches, either the one I showed, the two I showed before, either decomposing the field and using rotation matrices, or using adaptive step size ODE solvers. And that has certain disadvantages and advantages. It's probably less efficient, but much more easy to implement and to extend. And that is actually the way the general simulator works, which I will present in the remainder of this talk. And most of the simulators I showed in the beginning actually use the different approach. That means decompose the B field and apply rotation matrices, which is in many ways more efficient, but much more difficult to generalize. And the approach we were taking is to try to do something which is really very general and multi-purpose. So we wanted to come up with a simulator which is basically gives most general description of the physics. So it needs numerical solutions of the Bloch equation, but it should also reflect the hardware of modern MRI systems, and of course include all the nasty effects which, for example, distort our images either due to off-resonance coming from the subject itself, like the air tissue interfaces, or coming from the gradient system, for example, which might be nonlinear or whatever. So all these effects should be included. Then, of course, should be very easy to design your own experiments. That means it should require little expert knowledge, such as programming a Siemens scanner. Yeah, so that should be much more easy, ideally without any programming. And last but not least, as we always want to have, it should be extensible and reusable. So it should be some sort of modern software design involved, using design patterns, for example. And of course, it should be open source, such allowing reproducible research. So that were basically the things we had in mind many years ago, and there were no actually projects around, and therefore we started our own and came up with the GEMRA software. And you find all the information on the website, and I will now quickly go through some of the main properties of that software and what you actually can do with it. So with respect to the physics, what is covered, as I said, it's solving the general Bloch equations numerically in the rotating frame. This is actually best done in cylindrical coordinates for the reason that if we simulate off resonances with a an adaptive step size integrator, that we typically would like to have smooth solutions which allows to use large steps. And this is the case for cylindrical coordinates, but not for Cartesian coordinates, where the solution rapidly oscillates and we cannot use large step size. So that's one specific detail, maybe nothing you should bother about. One thing, of course, what we want to simulate is parallel receive and transmit. Well, parallel receive, everyone knows. That's required for parallel imaging. That's the multi-call data you typically get from your scanner. And that, of course, you also want to be able to simulate. So that's basically meaning we have a signal equation with multiple receivers. Well, if you're additionally interested in high field MRI, you may have heard this approach is also taken to the transmit side, because we typically have at high field a distorted excitation field, and that can be cleaned up or mitigated with multiple transmitters. So that's something we want to be able to simulate as well. So this is a simulation of multiple receivers in the top row. And that is interesting, especially, for example, testing reconstruction algorithms by knowledge of the receive fields. Bottom row shows a selective excitation, two-dimensional selective excitation example with multiple transmitters. Typically, high field systems nowadays have maximum 8 transmit channels. There exists also some 16-channel systems for human imaging, but in simulations you can easily go further and test whether 32 or 128 channels are useful to have. And doing something like this in real life would be really very, very expensive, yeah? But it doesn't cost too much in simulations. Then, of course, it is possible to define the object in GEMRIS using different with relaxation times and also including susceptibility or chemical shift. So we have predefined objects, for example, a brain available, and also user-defined samples can be used. Actually, I just want to show the... Oh, sorry, I have still 15 minutes left, so that should be fine. Yeah, so off-resonances can be, of course, also simulated. And T2 star can be simulated. T2 star is typically most easily simulated using a Lorentzian distribution of off-resonances of each spin that then nicely simulates this faster decay of the signal, switching back and forth. So this is simulating without T2 star. So we just have the T2 decay, including T2 star. We have a quicker decay. If we actually do not have a lot of spins involved, we see it no longer looks so much exponential. So that again shows lots and lots of spins need to be involved for realistic simulations. Other thing we implemented is any kind of spatio-temporal variations of the object that can be used for simulating motion, seen in the left, or simulating flow, seen in the middle, or also simulating diffusion of spins. Additionally, we may not just want to change the position of the object over time, but maybe also the relaxation times, for example, to simulate contrast agents or to simulate bold, which would change T2 star in a localized away temporarily. So all that can be done, but that would be all variations coming from the object. But of course, there are also variations which come from the system itself. So for example, eddy currents or any kind of nonlinear encoding fields as we have them in MRI present very often. Yeah? Especially eddy currents are nasty, especially in diffusion imaging. They can distort the image. Nonlinear gradient fields, you may or may not be aware of that each and every MR scanner has is not perfectly linear. Yeah? We typically have some warping of the images directly done online on the scanner. If you turn it off, you will recognize that your images are heavily distorted since there are some gradient nonlinearities involved. All this can be very easily also simulated in GEMRIS, even on an event basis. That means for each and every gradient event, you can specify the according eddy currents or also the non-linear behavior. So this is an example of eddy currents in the top row where you, for EPI, where you see the typical ghosting in EPI, and that can be on the same axis or also on different axes. That means cross eddy current cross terms. And in the bottom row, you see something what is called the concomitant field. It's a very specific field, of course, strongly exaggerated here in these examples, but that can be present as well. Especially, actually, concomitant fields are problematic at lower field strengths. So much about the physics. The GEMRIS itself is implemented in C++. It's especially well suited for multiple CPUs. It uses an adaptive time-stepping solver, as I said before. Important is pulse sequences can be easily defined by the user, which is actually especially easy because it involves evaluation of symbolic mass. And then there are MATLAB graphical user interfaces available. We're currently working on to make them available in Python as well, which is a bit of tedious work, but hopefully we have a stable version soon. It's all open source, it's on GitHub, and there's also a Google group for discussing issues. Yeah, this is the parallelization. Well, that's actually very straightforward master-slaves parallelization, where each node works on a sub-sample and finally all sub-signals are collected and the total signal is generated. Performance profiling, maybe also not too interesting, just important to note that the parallelization is nearly optimal because it's very easy to parallelize. These are the graphical user interfaces for sequence design. You actually can also lay out your own RF coils for multi-channel acquisition, and then finally one graphical user interface for the simulation. All this is just for convenience. You can do all the things also from the command line, and you use, I don't know, for example, your own Python tools to visualize results. It's actually, everything is constructed in XML, and data, simulated data, is stored in HDF5. Most time we spend on the sequence design, which follows some observer design pattern. I don't want to go into detail, but the nice thing is that it renders specialized implementations needless, so we have very, very few modules. And then with that you can basically do everything. So this is, for example, source code of an EPI sequence. So it's not really coding, it's more like giving a few simple instructions. But definitely you would need some time to get acquainted to it, but the learning curve is really flat. There are detailed, so there is documentation available, these detailed descriptions of the user interfaces, also tutorials available, and I will end my talk with giving a few examples. So this is example of basic artifacts, also, oops, okay, movie is not running, but on the top right, this is example of motion, realistic motion, which can be simulated, and on the top, on the bottom right, some simulation on selective excitation. So this is typical examples interesting for a physicist. There were also more real-world simulations done with GEMRIS. So this was simulating the accuracy of carotid plaque MRI with this simulator, which had been done in the past. And very final thing I wanted to show is that actually you can also use GEMRIS to run sequences on real hardware. So this is an interesting project which is called PulseSec, and which also nicely fits to the theme of this workshop here, OpenMR. So the idea of PulseSec was to make MR sequences openly available, which is of course a very difficult task, because typically vendors like Siemens and Philips don't like it very much if their sequence environment is programming environment is not freely available, but very much hidden to the users, and you have to sign special research agreements typically with the vendor. And yeah, the PulseSec thing is a nice framework, because it basically makes one sequence transferable from one vendor to the other, because it basically boils down to a very simple instruction, as you see on the left, of which then runs on each and every hardware. For example, Siemens, GE, and Bruker is so far supported by PulseSec. Yeah? Philips not yet, but I think they are working on it. So that means you basically have different design tools. GEMRIS is just one of them, which can generate such a PulseSec sequence file, which you then can run on the scanner. Yeah? So this, on Siemens, it would look like this. If you use GEMRIS as a design tool, you generate this PulseSec file, run it on the Siemens scanner, collect the raw case-based data. Yeah? So raw data is not the image. Then you do some custom reconstruction or use some software, open source software such as BART or Gadgetron to do the reconstruction, and finally get an image. If you have used GEMRIS as a design tool, you could also do then do a simulation of the same pulse sequence and see how it coincides with a real image, which is very nice. In this case, that was an example from the original paper. Very, very finally, I wanted to give one example from our group where we utilized this approach and using PulseSec. And this was a project we started 3 years ago. We had some idea to do a better reconstruction, or let's say a different way to reconstruct wave-Kuiper data. Wave-Kuiper is a nice acquisition approach, especially for anatomical imaging, and developed by the guys from the Martino Center in Boston. And it involves in the pulse sequence these sort of waves, as you can see them on the bottom picture. In K-space, that would look like this. You get these sort of corkscrew trajectories which improve signal to noise. Yeah, so let's say it like this. So that was when we looked at this original paper, we thought, well, that's cool, but we could do a different way to reconstruct it. But then you also need to know very exactly what your gradient system is doing. And because we have this field camera, we can measure the gradients and then do potentially a correction. So this is, of course, a huge project for a PhD student, because if you also have to implement the sequence on the Siemens scanner, but because we have this PulseSec interface, the PhD student could just simply program the scanner using this graphical user interface. And yeah, these were some intermediate results showing the importance of the corrections of the trajectories. And then just 3 years later, the paper was published. And that was really a single PhD project. And Yolanda, the first author, had no idea and still has no idea how to program a Siemens scanner. Yeah? But she simply used the GEMRIS framework for sequence development and PulseSec to port the sequence to the scanner. Yeah? So her project was image reconstruction, and still it was easily doable without help from any postdoc with huge knowledge on programming a Siemens scanner. Okay, so summing up what I talked about today. So simulating MR physics, there are many different approaches available. We have actually analytical solutions available only in very rare and special cases, and generally we have to apply some numerical solutions, and the preferred method depends, as always, very much on the application. Such simulations are typically very demanding computationally, so you have to think a lot before starting MR simulation. So how many spins are needed, how many spatial dimensions are needed, and often you should think if there are better ways than brute force numerical integration, because that really takes a long time. For example, if you're just interested in the amplitudes of the echo, you would favor a different approach using phase graphs than from what I showed today. What I showed today is more like a multi-purpose approach. So with general numerical integration, then many aspects of the physics can be covered. GEMRIS is only a simulation of the signal. It's not an image reconstruction. It's not for image reconstruction. For that, other tools are available. The main focus is on sequence design, where only a few building blocks are actually available, but those can be combined with very few limits and in a way which does not require any programming, but basically plugging things together. So learning curve is really flat, and then those sequences can also run on real hardware. Yeah, and the motivations why doing so I talked about in the beginning. So that's it. Thank you very much.
Questions?
Thank you for the talk. One question. In this simulator, so usually in MR scanner we have a subject. So how do you generate those images of brains that you showed?
So the objects which we have in GEMRIS are predefined objects. It's basically just a brain, but you can put in your own objects as a user-defined collection of spins, basically. Yeah. So we have a few predefined samples. One of them is a brain, which is basically derived from the MNI brain. Yeah.
So it's like a magnitude image that you use.
Sorry?
Magnitude MR image.
Well, what you need is basically a spatial distribution of spins with certain properties, such as relaxation times, proton density, susceptibility, chemical shift. Yeah. So and this such an object we derived from the MNI brain. Yeah, but certainly it's much more information than just a magnitude image. Yeah.
Okay.
How do we go to shoot like inference, right? Magnetization transfer or like say.
Oh, I didn't talk about magnetization transfer, which is a complicated topic on its own. But it's good that you're asking, because this is covered as well in GEMRIS. But this is no longer a simple Bloch equation, but it's a coupled Bloch equation. It's called the Bloch-McConnell equation. And then, yeah, you have chemical transfer of the magnetization from one pool to the other. So that's even more complicated. We have it in GEMRIS. It's not well documented. It is especially well documented in this recent MR simulator MRI lab. Yeah? So if you're interested in magnetization transfer and exchange, MRI lab would be a good way to start with. GEMRIS would be as well if you know how to, if you would just know how to use it. We're working on the documentation.
I have a question on your motivation introduction slide. There was something about sequence optimization and protocol optimization. I work now as a MR physicist in the clinic, so I need to do this almost every day. But as I understand, let's say I want to optimize a T2 a turbospin echo T2 weighted. That's a very common question, but I don't have the time on the scanner. But of course, then you would need the sequence from Siemens first, right? Before you can put it into...
Yeah, or something which is very close to it, let's say. I mean, that is often, of course, I mean, very depending on the application, yeah? But right, there is no easy conversion from Siemens to GEMRIS.
Okay.
The other way around works, but of course this way, actually there was written a tool, at least for Philips, to have a Philips sequence simulated in GEMRIS. Would be also not too difficult to do it for Siemens, but typically this results in very inefficient simulations, because then you have to step through the sequence in very small time steps, and this is exactly not how GEMRIS operates.
Okay.
So it's possible, but it's very, very inefficient.
Okay. So, yeah, and then my second question is about PulseSec. So are there any checks on before you run it on the scanner that you can't destroy any hardware or something?
Well, that would be more like a question for the PulseSec developer, so that's not... But, I mean, the PulseSec basically uses an interpreter sequence, which is written in Siemens IDEA, if you know that. And it basically follows the same checks Siemens IDEA follows. So you cannot easily exceed SAR limits, for example, but you could easily
do some nasty things with respect to mechanical resonances of the gradient system, which is not well checked for in Siemens. But that's more a problem of Siemens, I would say, than of Pulsec.
Okay, so we have to wrap up now. Thanks again.
Yeah,
Thank you very much.